Good morning. Today we are going to study about the topic IO input or output addressing capability and what are the special processor activities. In the previous session we have discussed about bus organization of 8086 microprocessor. In that we have three buses through which you can able to process the data in the microprocessor, which are data bus, address bus and control bus. Today we are going to study about IO addressing capability and some of the activities with which the processor will be able to perform. So IO addressing capability. So we already know how the addresses in your memory are being stored. Like we have four segment registers, so segments will be storing the data, and in the memory the segments are being stored and the corresponding address of the corresponding segments are being stored in the segment registers. So as you all know that we have address bus as 20-bit bus, nothing but 2 power 20, nothing but we have 1 megabyte of memory space, whereas the data bus are of 16-bit. So 16-bit nothing but 2 power 16 is equal to, we will get approximately as 64 kilobytes. So this is the IO space where you can able to store the data for IO part, which memory is 64 kilobytes. So as we have seen in the previous sessions that we can able to store a 8-bit address or we can able to store a 16-bit address. As we have seen in the previous sessions that we have a even memory bank and odd memory bank. Even memory bank nothing but low order memory bank, odd memory bank we can call as high order memory bank. Nothing but lower 8 bits can be stored in your even bank. Higher order or higher 8 bits can be stored in your odd bank. Right? So if the 8-bit IO address is there and we need to store in the IO space, then we can able to use, so the lower order is A0 to A7 and A8 to A15 is higher order. So if you are going for 8-bit, it will go for or lower order bank, or we can call as even bank. And A8 to A15 will be equal to 0. Similarly, A16 to A19 should be equal to 0 because we are going for IO addressing, and IO addressing can be of only 16 bits. Remaining 4 bits will be 0. Suppose if we are going for 16-bit address storage in the register TX, then the lower order 8-bit will be stored in the A0 to A7 registers and A8 to A15 will be stored as your higher order bits. So 16 bits can be stored in low order bank and even order bank. low order bank or even order bank, and high bank or odd bank, where A16 to A19 address will be 0. So depending upon the selection lines or selection points, it will select the logic and take the data and do the task. If we have the data which will be of your 8-bit or 16-bit, so if you have a data 8-bit, we will be using AL or AH. If you have a 16-bit data, we can use AX, which is accumulator. So lower order, which is D0 to D7, higher order D8 to D15. So you can take the data 8-bit and do the whatever the thing, depending upon these two operations: IO read, IO write. IO read bar, IO write bar. It is able to read from the input device and do the task, whereas IO write bar is for data writing into the IO space. So 8-bit, 16-bit, we can able to address, as it is a 16-bit addresses being available for your IO space of maximum 64 kilobytes of space. So if there's these 3 selection lines will be there in your pin configuration, which will be discussed in the next class or next session. So when 3 zeros, it tells that interrupt has been applied. So it acknowledges that interrupt has been occurred. 001, the IO will do the read operation. For 010, it will do the write operation. For 011, it will hold on up to certain time depending upon the processor. Halt. If it is 100, the opcode of the corresponding instruction will fetch. Opcode, nothing but a particular instructions will have some opcodes. So that opcode where we are, if you want to read, move nothing but it is moving the data from one register to other register. So move opcode will be fetching. For example, I am telling. So 100 opcode fetch. For 101 from memory, you can able to read the data or read the address or read the instructions. 110, then you can write into the memory as well. And for 3 ones, it means that your IO space or IO addressing is not in the active mode. So you can see here, 8086 processor can address up to 64 kilobyte IO registers, or I can call as 32 kilo word registers, because we have 16-bit that IO address, nothing but 2 power 16, which we can call as 64 kilobytes of IO registers or 32 kilo word registers. The IO address appears on the address lines from A0 to A15. Okay, because we have a 16-bit address for IO. As IO are 16-bit, so we can able to store a 16-bit address in the address lines from A0 to A15 for one clock cycle. One clock pulse is being applied. It may then be latched using the ALE signal. Address latch enable. Can able to enable the signal in order to go for next cycle. The upper address lines, which are the last, which are nothing but A16 to A19, will be 0 during all the IO operations. Getting your point here? Why they are 0? Because we have 16-bit IO addresses. So 16-bit, if you want to store, you have A0 to A15 for storage of 16-bit addresses. But we have address bus in our 8086 as 20 bits, so we can use A16 to A19 as well. But for doing the IO operations, for IO addressing, this A16 to A19 are at logic 0 level, or you can connect to ground. The 16-bit register DX is used as the 16-bit IO address pointer. Yeah, this is the general purpose register, which is known as data register, which is used as your basic pointer through which you can able to point the address of IO operation for in the DX register. So with full capability to address up to 64 kilobyte devices. Okay, so whatever the IO operations you want to perform, it points to the 16-bit address of the DX register. In memory mapped IO interfacing, the IO device addresses are treated as memory locations. So it will start from 40H. Even address bytes are transferred from D7 to D0, and odd address bytes are transferred on D8 to D15 lines. This is how your IO addressing lines will be performing the IO operations depending upon the addresses being stored in the memory from A0 to A15. Next topic is special processor activities of 8086. So what are the various special activities that 8086 can be able to perform? First activity is processor reset and initialization. So you can able to get a reset operation of the processor, and again how you can able to initialize. So if a clock pulse is being applied, so there will be automatically a positive edge and negative edge, right? So if reset is at positive edge, if the reset operation is being performed at positive edge, then it will stop the current execution. So if it is at positive edge, it will be positive, nothing but high, nothing but whatever the execution or whatever the operation it is performing, it stops there. If the reset is occurred at negative edge, then it will not only stop the current execution, but also it resets to the 0 position. Nothing but it resets the registers to the 0H. Except the CS value will be 4FH, and execution starts from the next one, CS value. After resetting, again where it will be initialized 4F0H continues up to 5F because the last address is 5F. Second one, see, processor reset, it will reset. If it is reset in the positive edge, it will stop the current execution. If it is in negative edge, it not only stops at the current execution, but also takes the value of the register to 000H, but the CS value will be 4Fh. After initialization, it starts from 4F0H to last 5Fh. Second one, halt. Halt means it will stop the execution process. It depends on minimum and maximum mode. Yeah, these things will be discussed in the next session. Minimum mode, nothing but we are halting, nothing but when S2, S1, S0 are as 0, 1, 1. Third, test and synchronization with external signal. Yeah, when external signal is being applied, how it will test and synchronize with the external signal. So 8086 has an extra facility to test during execution of wait instruction. Yeah, we have an instruction in the processor which is wait, which will be testing. So during testing, it will preserve the contents of register before execution of wait. Then CPU wait for test input. If it goes low, test input goes low. If this pin low, it further execution by processor. Otherwise, it waits for low for accept the signal, and it must be low for all 5 cycles. Simple. If any external signal is being applied, we have an instruction wait. So before wait is being executed, it preserves the contents of whatever the registers are being stored. After execution of the test, it goes to low. Nothing but it is waiting for testing. Until it becomes low, it doesn't accept the signal. So it must be low for all the cycles up to the external signal synchronization is being completed. Thank you.